Yeah,
不是我写的。
it's changed a little bit more. Like, I think 190 might be occupied, but now it's 198.
It's like it's total cluster. Yeah, no, the new ones are worse, dude. I know, but it's still worse.
Oh, possibly the DC one. Every single one.
Really?
DCEV, you know, see the picture?
I did not.
DCEV is
Start section the one north. Yeah. Start going back a little bit.
once I get there, I'm just there.
No, don't touch me.
So let's get started. Let's emphasize the concept of zero state response as to what a zero state response is. And if you have an impulse response of a system, LTI system, such that it can be described by an impulse response, which means that if you put in an impulse, out comes the output, which is just the impulse response. The zero state response of a system is a system such that there's no input for t less than 0. Okay, t less than a certain value. If input, say ft, is equal to 0 for t less than a certain value, say a, okay, which means that there was nothing there before you turn on the switch. Okay, and after you turn on the switch, when the input comes about, then the output would be given by this value. This value does not have any contribution for t from minus infinity. Okay, no contribution from this. So that means that there was no input to the system when t is still to minus infinity. And this is called a zero state response of the system, because it means that there's nothing there before you turn on the switch to send the input in. Okay? So you just have to memorize this concept. Then the book went about to talk about different ways of measuring impulse responses, and today we have to actually cover two sections in one lecture, which is section 10.1 and 10.2. So I'm going to go through these two sections quite rapidly. So measurement of the impulse response. So one way to measure the impulse response is actually to send in a unit step function as an input or maybe not as an input, but yeah, this will be your input. This is your impulse response. And this is your output, will be GT. So if this a unit step function that acts as an input, this is usually called your FT in the previous part of the course. So one way is to do this kind of experiment. It's a lot easier to construct a unit step function. Ideally, a unit step function looks something like this. This is what a unit step function looks like. But usually it has to be approximated in the lab. And maybe not ideally, it will look something like this, an approximate function of the unit step. But even in the lab, you might not get something like that. Okay, you will get something that looks more like if you were to construct a unit step function in the lab, it might look something like this. Okay, so this is what you have in the lab. Okay, and it's not truly a unit step function, but it's supposed to be a unit step function, and that is the most that you can have in the real world. In the real world, you cannot construct this, but you can construct something like this quite easily. So even an impulse function, if you differentiate this first function, if you differentiate it, it's supposed to get an impulse that looks something like that. Okay, but if you differentiate this one, you're going to get an impulse that looks something like this. Okay, this is an approximation. But if we differentiate something like this, it more or less looks something that goes to very large value and it maybe rings a little bit. Okay, so this is an approximation to the other function. So in the lab, you usually get something like this, and not quite close to the impulse. Yes?
To measure the impulse response, don't you give the input as a delta function? Because delta converted to h of t gives h of t, right?
Yeah, it's
Then why
quite
you
hard
do-
to construct a delta function. Okay, so most people just use a unit step function as an input. So if you have this as the output, how do I get the impulse response? That is quite easy. If I differentiate this with respect to t, it will be the differentiation of this with respect to the impulse response. But when I differentiate this, what do I get? I get the delta function. Okay. So one way to get the impulse response is to do this experiment, which is a lot easier to do in the lab. Okay. You hit the thing with a unit step function and look for the response. And after you measure the response, you take a standard derivative, you get an impulse response. Of course, you will never get something close to the exact impulse response. It will be just an approximation of the impulse response.
What if you pass this through the differentiator circuit we learned in the beginning of the
Right.
semester?
Right, differentiator circuit,
Then we get a delta function, right?
you get a delta function, but not an ideal one. Okay, you don't get an ideal one, you get an approximate. All this kind of thing can only be approximated in the lab. Okay, all this can only be approximately done in the lab. Okay. So there are a number of examples in section 10.1. Maybe I don't go through all of them, but only some of them. So if GT is given by e to the minus t ut, and this is the consequence of doing this convolution. Okay, if it's a consequence of doing this convolution, how do I find the impulse response? I just differentiate this. Okay, example 10.1. Okay, just differentiate this. I will get two terms. I will get minus e to the minus t ut plus e to the minus t delta t. I use the differentiation of the product rule, I get this. Okay? So this one is just equal to 1, right? This is just equal to 1. Let me see, 10.1. So this, using the shifting property of this, you can set this to be equal to 1, and this is just delta t. So the impulse response is just equal to delta t minus ut e to the minus t. So this is the impulse response of the system, if that is given to be your GT. Okay. There are several examples that are like that, and let me see if there are some better examples. Say you're asked to find the Fourier transform of the impulse response. Okay. Example 12.3, let's go through this example. It says that if ht is equal to 1 minus t e to the minus t u of t, find h omega. Okay, find h omega. And this is an exercise in Fourier transform. So You know how to actually do this exercise quite easily because h of omega is just h of t e to the minus j omega t dt. Use this Fourier transform rule. And then if you substitute that in, you get two terms. You will get minus infinity to infinity u of t e to the minus t e to the minus j omega t dt. This is the first term. And then the second term, you will get minus infinity to infinity t ut e to the minus t e to the minus j omega t dt. And we all know how to integrate the first term. The first term integrates to something like 0 to infinity e to the minus j omega plus 1t. Right? You can group the two exponents together and integrate this. This is equal to 1 over j omega plus 1, 0 to infinity. And you can evaluate this, and this will give you something like 1 over 1 plus j omega. Okay? The second term, how do you integrate the second term? When you have this linear t involved, it can be written as 0 to infinity minus 0 to infinity t e to the minus j omega plus 1 t dt. Okay, how do you integrate this term?
Why don't you use properties?
What is that?
Why don't you use properties? So we know that differentiation in time domain is multiplication by j omega. So multiplication of t in time domain should be differentiation in frequency domain, right?
Right, you can also invoke that property.
So wouldn't
Yes.
that be a more straightforward way of doing it?
Yeah, you can also invoke that property. Aditya is suggesting that why do we say that this is equal to minus the j omega plus 1. If I treat this as one variable, say u or maybe v or something, okay, and then differentiate with respect to that variable, then you actually get something like this with a plus sign e to the minus j omega plus 1t dt. Okay, you can write that expression. If you were to differentiate it with respect to this variable, you bring a t down, and the t down will give you that. You bring a minus t down. So we know how to integrate this one. Okay, we know how to integrate this one. So the final answer is treat this as a variable, and then treat this as a variable and differentiate that, and then you just get 1 over 1 plus j omega squared with a minus sign down front. Okay? So then you can combine the two terms. Combine the two terms together, you get what you want. You combine this term together with that term, you get the Fourier transform of the whole thing. Okay? Or you can do a table lookup. Is this in the table? T e to the minus t? Is this in the table?
That's duality, right?
What?
It's duality, right?
I know it's duality, but say if it's duality, can you invoke it? There are many ways to get the answer. You can use duality principle, you can use a number of things. Let me see, I never memorized the table, but it might be in your table. Okay? So are there any questions regarding on how to find the Fourier transform of this quantity? And then another thing I should emphasize is that you can have an LTI system. You can have an LTI system where this LTI is defined by h of t, And then if you have an input f of t, the output should become yt equal to f of t convolving with h of t. Okay? And this definition, which is also called a zero-state response, this is called a zero-state response for just the reason I have told you before. Okay, because you're supposed to assume that there's nothing in the input before you send in this signal. Okay, so this is called a zero-state response for that reason. And then it is important to note that ht transformed to h omega, and sometimes this transformation does not exist. It's possible that this transformation does not exist, or h omega does not exist sometimes. The case in point is what happens if h of t is something like this, ut times t. Okay, it is a function that looks like this. Okay, h of t looks something like this. And its Fourier transform does not exist. If you plug in that Fourier integral, you find that h of omega is equal to 0 to infinity t e to the minus j omega t, okay, dt. This integral does not converge, but this one does. This one does. Why does this converge? Why does it converge? And you get this finite answer, which is finite. But this one does not converge. Why does this one not converge? What happens to the integrand as t goes to infinity? It becomes bigger and bigger, multiplied by this exponential function whose amplitude is always 1. So the integrand always becomes bigger and bigger. Okay? But this one converges because it's multiplied by e to the minus t. So as you integrate, you can see that the value at t equal to infinity becomes smaller and smaller, and hence it converges. So h omega tends to infinity, or undefined. Okay, h omega is undefined for this particular problem over here. But yet you can put in inputs where this convolution integral exists. Let me give you an example. Say if my input f of t is an exponentially decaying function u of t e to the minus t. Okay? And then if you try to find the convolution of the integral, it still can be done. Okay? Then my y of t will be u of tau e to the minus tau convolving with this thing, which is u of t minus tau, t minus tau. Okay? I have this integral to perform, and I ask myself if the integral can be performed. It can, because this limit was from minus infinity to infinity, but when tau is equal to 0, it goes to 0, but when tau is larger than t, it goes to 0 as well. So this integral now becomes integration from this range to that range, but that thing becomes 1. Okay? And I can throw this out because this always becomes 1 in this range. So I have this integral to integrate. And do you know how to integrate the integral? Okay, the first term is just t e to the minus tau, 0 to t dt. The second term is a little bit trickier to integrate, tau e to the minus tau d tau. Okay? So first integral, what does it give me? Yes?
Why is there dt and a d tau?
D tau, yeah, this should be d tau, sorry. This should be d tau. Okay? So first integral, how would I integrate? If I integrate this, I will get something like t and then e to the minus tau with a minus sign 0 to t. This is what gives me for the first term. Okay? The second term, how do I integrate that?
Partial.
I can use integration by parts, right? I can use integration by parts, and then I can integrate this one first. Okay, if I apply the integration by parts rule, I will get tau e to the minus tau with a minus sign out front, and then 0 to t, and then I will have to differentiate this one, and then e to the minus tau, and because when I integrate this I get a minus sign, that goes away. This should be a t. So if I apply the integration by parts rule, I have that. And you see that I can get finite values all the time. Okay, so yt is definitely finite. So yt exists, even though h of omega does not exist. Okay, so there are situations where h of omega does not exist or undefined, but the convolutional integral still exists, and you can evaluate this and it becomes a finite number. Okay? So this is something peculiar about the LTI system, that h omega does not converge, but yet we can have a response. Okay, and then there are quite a number of examples in section 10.1. Okay, and then they ask you to test things like linearity, time invariance, and so on. So like you are given the test, such as this one over here. So if I do example 10.7, you're given that the output yt is f squared t plus capital T. Is this time invariant? Is this linear? Okay, time invariant can be proved very easily, that I suppose that f of t is the input to this system. Okay, f of t is the input to this system. And then you get a linear, not linear system, but just a system. And then the output is equal to this. So if I were to change my input to t minus t0, okay, what do you think the output is? By using this rule, the output would be y of t should be equal y of t, or maybe I could call this g of t. The new output would be f squared, if I make use of this rule, would be t minus t0 plus capital T. So this is in fact y of t minus t0. Is this kind of system time invariant? It is time invariant, right? Because I delay the input by a little bit, I get the output that is also delayed by a little bit. That is the definition of a time invariant system. Is this system linear? If I have two inputs, f1 of t gives me output f squared of t plus capital T. I have a second input. It gives me this as my output by using that rule over there. Now if I have a linear superposition of these two inputs, f1 of t plus k2 f2 of t, okay, is my output equal to, by using this rule, then the output I should have is actually k1 f1 t plus capital T plus k2 f2 t plus capital T whole thing squared. If I were to use this rule, if that is my input, that should be my output. Is this a linear superposition of the top two? Not at all, right? Not at all. Okay, so this is not linear. Okay, it's not linear because of this thing over here. Okay, so these are some of the tests that you have to go through in testing if the system is linear, time invariant, and so on. Are there any questions? Are there any questions on this kind of test? Okay, so let's go to section 10.2, which is actually more interesting. Okay, section 10.2 I think is more interesting. Is BIBO. Okay, not bimbo. Okay, BIBO. Okay. So what is BIBO? Bounded input, bounded output. Okay. This is a property of the linear time invariant system. Okay, and let's prove this property. That if your input is bounded, then the output is always bounded provided that the impulse response satisfies certain property. Okay, let's say that the output is equal to the impulse response convolving with the input. Okay, and by definition of what we had before, this is just equal to h of tau f of t minus tau d tau. And if the output is bounded, it means that this quantity must be a finite quantity, and that this must be equal to the magnitude of this quantity. Okay? And when you have to take the magnitude of a sum, an integral summation is a sum, what inequality would you invoke? You would want to make this less than or equal to something. What inequality would you invoke? Triangular inequality. Something similar to that. Okay? Something that grows from triangular inequality. Okay? So we know about the triangular inequality. And we have invoked something like that before too. Okay? So say if we have a complex number. A real number is a special case of a complex number. If something works for complex number, it also should work for real numbers. Okay, a complex number has real part and imaginary part. If I have a complex number, I can denote it by a point on a complex plane. Okay, so Z1 is one complex number. If I have another complex number, Z2, okay, I can denote it with another vector like this. And then the sum of Z1 and Z2, okay, is this complex number over here, this point over there. Okay? And this is how you add complex number on the complex plane. Very much like how you would add two-dimensional vectors. And from this picture, you can see that magnitude of Z1 plus Z2 is less than magnitude of Z1 plus magnitude of Z2. Can you see that? Magnitude of Z1 is one side of the triangle, magnitude of Z2 is the second side of the triangle. The third side of the triangle is Z1 plus Z2. And in this picture, the third side is always less than the sum of the other two sides. This is called a triangular inequality. So this can be generalized to Z1 plus Z2 plus Z3, okay, plus Zn. You can draw complex numbers on the complex plane very easily. You can add many, many complex numbers. Okay? And then the sum of this complex number, the magnitude of it is always less than the sum of its individual. Can you see this? Okay, this is the generalization of the triangular inequality for many, many sides of triangles with many, many sides. Not a triangle anymore, you call it a polygon. Okay, a polygon of many sides. Then you can take this idea and say that the summation of any number of numbers, the magnitude of this is always less than the sum of its magnitude. This is always true, and then you can generalize this to integrals. The x, z of x over infinitely many number is always less than the sum of this thing. Okay, this inequality is always satisfied. This is just a different way to express this inequality. So, if this is true, then I can say that this must be less than or equal to sum of the magnitude of its individual component. Okay, this is called it, I think it's called triangular inequality, or does it have a different name?
Cauchy-Schwarz.
Cauchy-Schwarz inequality?
I think it's a Cauchy-Schwarz.
Okay, I don't recall the exact name for it, but something like that. So that is always equal to, less than or equal to that. Okay? And let's assume that the input f of t is bounded by f max for all t. So this is bounded input. Okay, if the input is bounded, then I can also say that the magnitude of the product of two numbers, okay, this is also true. That the magnitude of h of tau, f of t minus tau, is always less than or equal to magnitude of h of tau times f of t minus tau. For real number, this is obvious. For complex number, it's not obvious. Okay, but this inequality also holds for complex numbers. Okay, I think it's called the Schwarz inequality in this case. Okay, this is always true. You want me to prove it, or is it obvious? Okay, so take any two complex numbers, multiply them together. The product is always less than or equal to the product of their magnitudes. Okay, so because of that, then they can take this and say that this is less than or equal to the tau, h of tau, f of t minus tau, the tau. And then I'm going to take this piece and say that this is always going to be less than f max. Okay, I can take this magnitude sign and say that this is always less than f max. Okay, then I can say that that thing over here, okay, is going to be less than or equal to f max. I take the maximum of its value outside, and then have this h tau, the tau, okay? I will only have this, okay? And if this h of tau is bounded, if h of tau is bounded such that this integration is bounded, okay? If I have the property that minus infinity to infinity d tau, h of tau, is less than or equal to a value gamma, say, then I would always have this thing less than or equal to gamma, which means that the output is bounded. Output is bounded by this thing. This implies that output y of t is bounded by f max gamma. So I have the case of a bounded output. If h of t is absolutely integrable, if h of t is absolutely integrable, which means that if you take the magnitude of h of t and integrate, that integral converges. Where have you seen this before? A function is absolutely integrable. Where have you seen this before? Calculus, linear algebra, but you also saw that in this course before. You remember? No, not exactly. Where have you seen this before? Fourier. When would the Fourier transform of a function exist? When the function is absolutely integrable. Okay, you remember that? Okay.
Told us to remember this future.
Okay, so if h of t is absolutely integrable, it also means that h of omega exists. Okay? That it exists. So, in order to get bounded input and bounded output, your input has to be bounded, your h of t has to be absolutely integrable. So h of omega has to exist, then the output is always bounded. Okay? So, but then, it turns out that this condition is stronger than it is. Okay? It's stronger than it is, which means that you get evil if and only if, and usually mathematicians write this as if, double F. Okay, if and only if h of t is absolutely integrable. Okay, if and only if also means a necessary and sufficient condition in logic.